A wind turbine is a device that converts kinetic energy from the wind into electrical power. A wind turbine used for charging batteries may be referred to as a wind charger. The result of over a millennium of windmill development and modern engineering, today's wind turbines are manufactured in a wide range of vertical and horizontal axis types. The smallest turbines are used for applications such as battery charging for auxiliary power for boats or caravans or to power traffic warning signs. Slightly larger turbines can be used for making small contributions to a domestic power supply while selling unused power back to the utility supplier via the electrical grid. Arrays of large turbines, known as wind farms, are becoming an increasingly important source of renewable energy and are used by many countries as part of a strategy to reduce their reliance on fossil fuels. History. Windmills were used in Persia as early as 200 BC. The wind wheel of Heron of Alexandria marks one of the first known instances of wind powering a machine in history. However, the first known practical windmills were built in Sistan, an eastern province of Iran, from the 7th century. These Paneman were vertical axle windmills, which had long vertical drive shafts with rectangular blades. Made of 6 to 12 sails covered in reed matting or cloth material, these windmills were used to grind grain or draw up water, and were used in the grist milling and sugarcane industries. Windmills first appeared in Europe during the Middle Ages. The first historical records of their use in England date to the 11th or 12th centuries, and there are reports of German crusaders taking their windmill-making skills to Syria around 1190. By the 14th century, Dutch windmills were in use to drain areas of the Rhine Delta. The first electricity-generating wind turbine was a battery charging machine installed in July 1887 by Scottish academic James Blythe at his holiday home in Marykirk, Scotland. Some months later, American inventor Charles F. Brush built the first automatically operated wind turbine for electricity production in Cleveland, Ohio. Although Blythe's turbine was considered uneconomical in the United Kingdom, electricity generation by wind turbines was more cost-effective in countries with widely scattered populations. In Denmark by 1900, there were about 2,500 windmills for mechanical loads such as pumps and mills, producing an estimated combined peak power of about 30 MW. The largest machines were on 24-meter towers with four-bladed 23-meter diameter rotors. By 1908 there were 72 wind-driven electric generators operating in the U.S. from 5 kW to 25 kW. Around the time of World War I, American windmill makers were producing 100,000 farm windmills each year, mostly for water pumping. By the 1930s, wind generators for electricity were common on farms, mostly in the United States where distribution systems had not yet been installed. In this period, high-tensile steel was cheap, and the generators were placed atop prefabricated open steel lattice towers. A forerunner of modern horizontal axis wind generators was in service at Yalta, USSR in 1931. This was a 100 kW generator on a 30-meter tower, connected to the local 6.3 kV distribution system. It was reported to have an annual capacity factor of 32%. Not much different from current wind machines. In the autumn of 1941, the first megawatt-class wind turbine was synchronized to a utility grid in Vermont. The Smith-Putnam wind turbine only ran for 1,100 hours before suffering a critical failure. The unit was not repaired because of shortage of materials during the war. The first utility grid-connected wind turbine to operate in the UK was built by John Brown and Company in 1951 in the Orkney Islands. Despite these diverse developments in fossil fuel systems almost entirely eliminated any wind turbine systems larger than supermicro size. In the early 1970s, however, anti-nuclear protests in Denmark spurred artisan mechanics to develop microturbines of 22 kW. The organizing of owners into associations and cooperatives led to the lobbying of the government and utilities, which incentivized larger turbines throughout the 1980s and afterwards. Local activists in Germany, nascent turbine manufacturers in Spain, and large investors in the US in the early 1990s then lobbied for policies which stimulated the industry in those countries. Later companies formed in India and China. As of 2012, Danish company Vestas is the world's biggest wind turbine manufacturer. Resources. A quantitative measure of the wind energy available at any location is called the wind power density. It is a calculation of the mean annual power available per square meter of swept area of a turbine, and is tabulated for different heights above ground. Calculation of wind power density includes the effect of wind velocity and air density. Color-coded maps are prepared for a particular area described, for example, as mean annual power density at 50 meters. In the United States, the results of the above calculation are included in an index developed by the National Renewable Energy Laboratory and referred to as an REL class. The larger the WPD calculation, the higher it is rated by class. Classes range from Class 1 to Class 7. Commercial wind farms generally are sited in Class 3 or higher areas, although isolated points in an otherwise Class 1 area may be practical to exploit. Wind turbines are classified by the wind speed they are designed for, from Class A to Class 4, with A or B referring to the turbulence. Efficiency. Not all the energy of blowing wind can be harvested, since conservation of mass requires that as much mass of air exits the turbine as enters it. Bette's law gives the maximal achievable extraction of wind power by a wind turbine as 59% of the total kinetic energy of the air flowing through the turbine. Further inefficiencies, such as rotor blade friction and drag, gearbox losses, generator and converter losses, reduce the power delivered by a wind turbine. Commercial utility-connected turbines deliver about 75% of the Bette's limit of power extractable from the wind, at rated operating speed. Efficiency can decrease slightly over time due to wear. Analysis of 3128 wind turbines older than 10 years in Denmark showed that half of the turbines had no decrease, while the other half saw a production decrease of 1.2% per year. Types. Wind turbines can rotate about either a horizontal or a vertical axis, the former being both older and more common. Horizontal axis. Horizontal axis wind turbines have the main rotor shaft and electrical generator at the top of a tower, and must be pointed into the wind. Small turbines are pointed by a simple wind vane, while large turbines generally use a wind sensor coupled with a servo motor. Most have a gearbox, which turns the slow rotation of the blades into a quicker rotation that is more suitable to drive an electrical generator. Since a tower produces turbulence behind it, the turbine is usually positioned upwind of his supporting tower. Turbine blades are made stiff to prevent the blades from being pushed into the tower by high winds. Additionally, the blades are placed a considerable distance in front of the tower and are sometimes tilted forward into the wind a small amount. Downwind machines have been built, despite the problem of turbulence, because they don't need an additional mechanism for keeping them in line with the wind, and because in high winds the blades can be allowed to bend, which reduces their swept area and thus their wind resistance. Since cyclical turbulence may lead to fatigue failures, most HAWTs are of upwind design. Turbines used in wind farms for commercial production of electric power are usually three-bladed and pointed into the wind by computer-controlled motors. These have high tip speeds of over 320 km per hour, high efficiency, and low torque ripple, which contribute to good reliability. The blades are usually colored white for daytime visibility by aircraft and range in length from 20 to 40 meters or more. The tubular steel towers range from 60 to 90 meters tall. The blades rotate at 10 to 22 revolutions per minute. At 22 rotations per minute the tip speed exceeds 90 meters per second. A gearbox is commonly used for stepping up the speed of the generator, although designs may also use direct drive of an annular generator. Some models operate at constant speed, but more energy can be collected by variable speed turbines which use a solid-state power converter to interface to the transmission system. All turbines are equipped with protective features to avoid damage at high wind speeds, by feathering the blades into the wind which ceases their rotation, supplemented by brakes. Vertical axis design. Vertical axis wind turbines have the main rotor shaft arranged vertically. One advantage of this arrangement is that the turbine does not need to be pointed into the wind to be effective, which is an advantage on a site where the wind direction is highly variable, for example when the turbine is integrated into a building. Also, the generator and gearbox can be placed near the ground, using a direct drive from the rotor assembly to the ground-based gearbox, improving accessibility for maintenance. The key disadvantages include the relatively low rotational speed with the consequential higher torque and hence higher cost of the drivetrain, the inherently lower power coefficient, the 360-degree rotation of the aerofoil within the wind flow during each cycle and hence the highly dynamic loading on the blade, the pulsating torque generated by some rotor designs on the drivetrain, and the difficulty of modeling the wind flow accurately and hence the challenges of analyzing and designing the rotor prior to fabricating a prototype. When a turbine is mounted on a rooftop, the building generally redirects wind over the roof and this can double the wind speed at the turbine. If the height of a rooftop-mounted turbine tower is approximately 50% of the building height, it is near the optimum for maximum wind energy and minimum wind turbulence. Wind speeds within the built environment are generally much lower than at exposed rural sites. Noise may be a concern and an existing structure may not adequately resist the additional stress. Subtypes of the vertical axis design include Darius wind turbine, egg beater turbines, or Darius turbines, were named after the French inventor, Georges Darius. They have good efficiency, but produce large torque ripple and cyclical stress on the tower, which contributes to poor reliability. They also generally require some external power source, or an additional Savonius rotor to start turning, because the starting torque is very low. The torque ripple is reduced by using 3 or more blades, which results in greater solidity of the rotor. Solidity is measured by blade area divided by the rotor area. Newer Darius-type turbines are not held up by guy wires but have an external superstructure connected to the top bearing. Gyomel, a subtype of Darius turbine with straight, as opposed to curved, blades. The cyclic turbine variety has variable pitch to reduce the torque pulsation and is self-starting. The advantages of variable pitch are, high starting torque, a wide, relatively flat torque curve, a higher coefficient of performance, more efficient operation in turbulent winds, and a lower blade speed ratio which lowers blade bending stresses. Straight, V, or curved blades may be used. Savonius wind turbine, these are drag-type devices with 2 scoops that are used in anemometers, Flettner vents, and in some high-reliability low-efficiency power turbines. They are always self-starting if there are at least 3 scoops. Twisted Savonius is a modified Savonius, with long helical scoops to provide smooth torque. This is often used as a rooftop wind turbine and has even been adapted for ships. Another type of vertical axis is the parallel turbine, which is similar to the cross-flow fan or centrifugal fan. It uses the ground effect. Vertical axis turbines of this type have been tried for many years. A unit producing 10 kW was built by Israeli wind pioneer Bruce Brill in the 1980s. Design and construction. Wind turbines are designed to exploit the wind energy that exists at a location. Aerodynamic modeling is used to determine the optimum tower height, control systems, number of blades and blade shape. Wind turbines convert wind energy to electricity for distribution. Conventional horizontal axis turbines can be divided into 3 components: the rotor component, which is approximately 20% of the wind turbine cost, includes the blades for converting wind energy to low-speed rotational energy. The generator component, which is approximately 34% of the wind turbine cost, includes the electrical generator, the control electronics, and most likely a gearbox, adjustable speed drive or continuously variable transmission component for converting the low-speed incoming rotation to high-speed rotation suitable for generating electricity. The structural support component, which is approximately 15% of the wind turbine cost, includes the tower and rotor yaw mechanism. A 1.5 MW wind turbine of a type frequently seen in the United States has a tower 80 meters high. The rotor assembly weighs 22,000 kilograms. The nacelle, which contains the generator component, weighs 52,000 kilograms. The concrete base for the tower is constructed using 26,000 kilograms of reinforcing steel and contains 190 cubic meters of concrete. The base is 50 meters in diameter and 2.4 meters thick near the center. Among all renewable energy systems, wind turbines have the highest effective intensity of power harvesting surface because turbine blades not only harvest wind power, but also concentrate it. Unconventional designs. One E66 wind turbine at Windpark Oltiem, Germany, carries an observation deck, open for visitors. Another turbine of the same type, with an observation deck, is located in Swaffham, England. Airborne wind turbines have been investigated many times but have yet to produce significant energy. Conceptually, wind turbines may also be used in conjunction with a large vertical solar updraft tower to extract the energy due to air heated by the sun. Wind turbines which utilize the Magnus effect have been developed. The ram air turbine is a specialist form of small turbine that is fitted to some aircraft. When deployed, the RAT is spun by the airstream going past the aircraft and can provide power for the most essential systems if there is a loss of all only-board electrical power. Wind turbines on public display. A few localities have exploited the attention-getting nature of wind turbines by placing them on public display either with visitor centers around their bases, or with viewing areas farther away. The wind turbines themselves are generally of conventional horizontal axis, three-bladed design, and generate power to feed electrical grids, but they also serve the unconventional roles of technology demonstration, public relations, and education. Small wind turbines. Small wind turbines may be used for a variety of applications including on or off-grid residences, telecom from towers, offshore platforms, rural schools and clinics, remote monitoring and other purposes that require energy where there is no electric grid, or where the grid is unstable. Small wind turbines may be as small as a 50-watt generator for boat or caravan use. Hybrid solar and wind-powered units are increasingly being used for traffic signage, particularly in rural locations, as they avoid the need to lay long cables from the nearest mains connection point. The U.S. Department of Energy's National Renewable Energy Laboratory defines small wind turbines as those smaller than or equal to 100 kilowatts. Small units often have direct drive generators, direct current output, aeroelastic blades, lifetime bearings and use a vane to point into the wind. Larger, more costly turbines generally have geared power trains, alternating current output, flaps and are actively pointed into the wind. Direct drive generators and aeroelastic blades for large wind turbines are being researched. Wind turbine spacing. On most horizontal wind turbine farms, a spacing of about 6 to 10 times the rotor diameter is often upheld. However, for large wind farms distances of about 15 rotor diameters should be more economically optimal, taking into account typical wind turbine and land costs. This conclusion has been reached by research conducted by Charles Manevo of the Johns Hopkins University, and Johan Meyers of Leuven University in Belgium, based on computer simulations that take into account the detailed interactions among wind turbines as well as with the entire turbulent atmospheric boundary layer. Moreover, recent research by John DeBerry of Caltech suggests that vertical wind turbines may be placed much more closely together so long as an alternating pattern of rotation is created allowing blades of neighboring turbines to move in the same direction as they approach one another. Wind turbine braking system. Wind turbines' disc pads are formulated with ceramic compounds and brass chips instead of the commonly used semi-metallic pad steel fibers. The brass chips are able to transfer heat into the ceramic pad which acts like a heat sink then dissipates back into the rotor and atmosphere once the brakes have been released. Along with time-released lubricants allowing the ceramic pads to handle higher brake temperatures with less heat fade, protecting the calipers and pistons. A cooler running disc pad generates less wear on both pads' rotors. Records. Largest capacity. The Vestas V164 has a rated capacity of 8.0 MW, has an overall height of 220 am, a diameter of 164 am, and is the world's largest capacity wind turbine since its introduction in 2014. At least 5 companies are working on the development of a 10 MW turbine. Largest swept area. The turbine with the largest swept area is the Samsung S7.0-171, with a diameter of 171 am, giving a total sweep of 22,966 am2. Tallest. Vestas V164 is the tallest wind turbine, standing in Østerild, Denmark, 220 meters tall, constructed in 2014. Highest tower. Fuller current Air install a 2.5 MW turbine on a 160 m lattice tower in 2003. Largest vertical axis. La Nordeus wind farm in Cap-Chat, Quebec has a vertical axis wind turbine named a per-mille, which is the world's largest at 110 am. It has a nameplate capacity of 3.8 MW. Largest two-bladed turbine. Today's biggest two-bladed turbine is built by Mingyang Wind Power in 2013. It is a CD 6.5 MW offshore downwind turbine, designed by Aerodyn Energy System. Most southerly, the turbines currently operating closest to the South Pole are 3 Anakin E33 in Antarctica, powering New Zealand's Scott Base and the United States McMurdo Station since December 2009, although a modified HR-3 turbine from Northern Power Systems operated at the Amundsen Scott South Pole Station in 1997 and 1998. In March 2010, Saipf designed, built and installed a wind turbine in Argentine Mambio Base. Most productive. 4 turbines at Ryan Wind Farm in Denmark share the record for the most productive wind turbines, with each having generated 63.2 GWh by June 2010. Highest situated. Since 2013, the world's highest situated wind turbine is made by United Wind Power China Guodian Corporation, installed by the Longyuan Power and located in the Nak country, Tibet, around 4,800 meters above sea level. The site uses a 1,500 kilowatt wind turbine designed by Aerodyn Energy System. Largest floating wind turbine, the world's largest Euro, and also the first operational deep-water large-capacity Euro floating wind turbine is the 2.3 MW wind currently operating 10 km offshore in 220-meter deep water, southwest of Karmøy, Norway. The turbine began operating in September 2009 and utilizes a Siemens 2.3 MW turbine. See also: External links, Harvesting the Wind, Wind Projects, Guided or on Wind Energy, U.S. Wind Turbine Manufacturing, Federal Support for an Emerging Industry, Congressional Research Service, Wind Energy Technology, World Wind Energy Association, Wind Turbine Simulation, National Geographic, Airborne Wind Industry Association International. The world's 10 biggest wind turbines. The Tethys database seeks to gather, organize and make available information on potential environmental effects of offshore wind energy development. Further reading: Tony Burton, David Sharp, Nick Jenkins, Irvin Bossone, Wind Energy Handbook, John Wiley & Sons, 1st edition, ISBN 0-471- 48997-2, Darrell, Dodge, Early History through 1875, TeloNet Web Development, Copyright 1996 Euro 2001, Robert Gash, Jock&Twell, Wind Power Plants. Fundamentals, Design, Construction and Operation, Springer 2012 ISBN 978-3-642-22937-4. Eric Howe, Wind Turbines, Fundamentals, Technologies, Application, Economics. Springer, 2013 ISBN 978-3-642-27150-2. Siegfried Heyer, Grid Integration of Wind Energy Conversion Systems. Wiley 2006, ISBN 978-0-470-86899-7. Peter Jameson, Innovation in Wind Turbine Design. Wiley & Sons 2011, ISBN 978-0-470-69981-2. David Sparrow, Wind Turbine Technology, Fundamental Concepts in Wind Turbine Engineering, 2nd edition, ASME Press, ISBN 9780791802601, A. Lewis Schaffakzeig, Understanding Wind Power Technology, Wiley & Sons 2014, ISBN 978-1-118-64751-6. Hermann Josef Wagner, Jotame Martha, Introduction to Wind Energy Systems. Basics, Technology and Operation. Springer 2013, ISBN 978-3-642-32975-3. Ursen Erdem, Wind Turbine Industrial Applications, References.